Professor Dave here. Let's do some dating.
He knows a lot about the science stuff. Professor Dave explains.
In a previous tutorial, we learned all about the different nuclear reactions that nuclides can undergo, which helped us understand what radioactivity and radiation are. If this sounds unfamiliar, definitely check out that tutorial first, as all of that knowledge will be assumed in this one. If we are up to speed, then we now understand that various radioactive nuclei will decay at different rates depending on their half-lives, and we have developed a number of practical applications for this phenomenon in a variety of scientific and medical fields. One such application is something called radiometric dating. So let's learn about this now. Radiometric dating is a technique we have developed that takes our knowledge of the half-lives of various nuclei and uses that information to determine the age of a particular object, including things like fossils and ancient artifacts. A very common kind of radiometric dating utilizes carbon-14, a radioactive isotope of carbon, which is accurate in dating artifacts with an age of up to around 50,000 years. This is useful because carbon is such a common element, especially in living things, and anything with carbon atoms will have a trace amount of carbon-14. So this allows us to date a wide variety of objects. Carbon-14 forms in the upper atmosphere when nitrogen-14 collides with neutrons from cosmic rays in space, and although the vast majority of carbon is carbon-12, and most of the rest is carbon-13, there is a trace amount of carbon-14 anywhere there is carbon on Earth, including the carbon dioxide in the atmosphere. Carbon dioxide is absorbed by plants, and plants are eaten by animals, so living organisms, which are constantly bringing in material and expelling waste, will display the same ratio of carbon-12 to carbon-14 as is found in the atmosphere. But when an organism dies and all cellular processes come to a halt, no more material will be going in or out of that organism, so no new carbon-14 can become present, and all of the carbon is locked in place. Carbon-14 will then undergo beta emission to become nitrogen-14 again, thus gradually decreasing the amount of carbon-14 in the organism. And this process displays a half-life of 5,730 years. That means that if we find a wooden artifact made from a once living tree and then use a mass spectrometer to determine that the ratio of carbon-14 to carbon-12 in that artifact is half of what it is in a currently living tree, that object must be around 5,730 years old, because half of the carbon-14 present when the wood was part of the living tree has already decayed. Of course, if any more than 10 or so half-lives have elapsed, this technique becomes less and less reliable. However, there are many other radioactive nuclei that we can use that have totally different half-lives and thus allow us to date objects of a wide variety of ages. Potassium, argon, lead, these all have radioactive isotopes that can be examined if an object in question contains appreciable amounts of that element, and many of these allow us to date objects much older than 50,000 years. Uranium-238 is commonly used to determine the age of certain rocks, including the oldest rocks on Earth, since this particular nuclide has a half-life of 4.5 billion years. Uranium-238 undergoes a decay series to produce lead-206, so we simply measure the ratio of uranium-238 to lead-206 in a rock to get its age. There are those who question the accuracy of such methods, and indeed there must be confidence that an object has not had its levels of these nuclei altered over time somehow, in order to trust the results of these techniques. But scientists are not naive. They know how to be rigorously empirical. Precision is enhanced dramatically when measurements are taken using two completely different radioactive nuclei. For example, if uranium dating is used to find that a rock is 3.62 million years old, And then lead dating is used to find that the same rock is 3.56 million years old. It is extremely unlikely that the rock is not approximately that age, because these are totally disparate materials, and the agreement of these measurements corroborates the age of the rock. These are the kinds of methods we have used to determine the approximate age of the Earth, which is around 4.6 billion years old. This is a value that really puts our existence into perspective and truly demonstrates the power of science in helping us understand the universe. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.